Okay, our next problem says to find a formula for the sum of the interior angles of a convex polygon with n sides. Now, if you remember, convex is kind of like our regular shapes, where it means none of the interior angles are greater than 180. And a polygon with n sides just means any amount of sides we can think of. Now, to find one of the best ways to find formulas for things is to start with simple cases. So the simplest polygon I can think of is the triangle. Now, when we look at the triangle, we know that the sum of the interior angles is 180 degrees. We've proven that way back when. So now let's look at another one step in complexity, a four-sided polygon, some sort of quadrilateral. Now we have shown, and it doesn't have to be like a parallelogram, it can be a square or a rectangle or a rhombus, but some sort of quadrilateral. And we have shown that all quadrilaterals have a sum of an interior at 360 degrees. But how did we show that this was true? Well, we took this quadrilateral and connected the diagonals and created two triangles out of the problem. Alright, now let's continue on. In the previous problem, we had a five-sided figure. So we'll just draw something with five sides. So that's 1, 2, 3, 4, 5. And we had proven that the sum of these interior angles was 540 degrees. Well, how did we do that? Again, we just connected the diagonals and we came up with a figure with three triangles. And we start to see a pattern. The base polygon has 180. The next step up is 360. And if I add 180 with 360, we get 540. And we get another triangle in our figure. So let's do six sides. 1, 2, 3, 4, 5, and 6. And we will draw our triangles from one of the vertices. And what do you know? We have now four triangles. And by the same logic, we would end up getting that, well, we would just add 180 with 540. And that would get us 720. Now, what seems to be the pattern, because we could go on and do this process for forever. And if we were to, we could come up with any number of shapes of some like weird looking design where we would just keep drawing triangles for like any number of shapes, even something weird like this shape here. It's definitely a polygon, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9 sides. And if it's 9 sides, it has 1, 2, 3, 4, 5, 6, 7 triangles. Well, what seems to be the pattern? 3 sides is 1 triangle, 4 sides is 2 triangles, 5 sides is 3 triangles, 6 sides is 4, 9 is 7. So if we list that out, so we have sides and triangles. So 3 sides gives us 1 triangle. 4 gives us 2. 5 gives us 3. 6 gives us 4. 9 gives us 7, and we could probably figure out the rest. 7 would give us 5. 8 would give us 6. So what seems to be the pattern? Well, the number of triangles is always 2 less than the number of sides. So if we have a polygon with n sides, then that means we have 2 less than n triangles. So n sides produces n minus 2 triangles. And the interior angles of those triangles is 180. So if I want to find the sum of the interior angles of an n-sided figure, my logic would be to take the number of triangles and add them up, or take the number of triangles and multiply with 180. So our formula is going to end up being 180 degrees times our number of triangles, which would be n minus 2. And we could put this to work. 3 sides, 3 minus 2 is 1, times 180 is 180. 4 sides, n would be 4. 4 minus 2 is 2, times 180 is 360. And we can see that this formula would fit for each of these shapes. Now it's very tough to actually prove this is true, so we're just going to kind of accept it and learn our first important theorem, that the sum of the interior angles in an n-sided polygon is 180 times n minus 2 degrees. And with a little bit of logic, we can understand that in a regular n-gon, where all the interior angles are the same, each interior angle has a measure of 180 minus or times n minus 2 degrees divided by n for the number of vertices. Again, it's a little bit weird to understand, but when we actually practice it, it'll make more sense. When we find the individual angle, what each interior angle is worth in a regular n-gon only, just take that total sum and divide by the number of vertices. And we'll see exactly how this process works in the next problem.